In this question, we have a rotor, rigid rotor. So this rigid rotor is made up of a massless rod with two masses, okay, M1 and M2, okay, and we are given that uh, the um, moment of inertia of the situation, okay, about the center of mass is M1 M2 divided by M1 plus M2 A square. Okay, so this M1 M2 divided by M1 plus M2 is the reduced mass, which I'm going to call it mu. Okay, A square. Okay, mu is the reduced mass. Okay, yeah. So in part A, there are 4 parts in this question. So basically, we want to find the energy eigenvalues, the wave function, and the energy spectrum of the situation. And then we use this idea to estimate the bond length of carbon monoxide. Okay. Okay, so in part A, we want to show that the allowed energies of the energy of the rigid rotor. Okay, so what's the first thing I will try to derive why the moments of inertia is that. Okay, so if we take origin at M1, right, and then the center of mass will be M2A divided by M1 plus M2, right? So could be somewhere here is the center of mass, okay? And then this is M2A divided by M1 plus M2, and then here would just be A minus M2A divided by M1 plus M2, okay? Right, so then the I of the center of mass, the I about the center of mass, because the rotation is about the center of mass, okay, will be m1 times the distance square. So this is m2a divided by m1 plus m2 square and plus m2 a minus m2a divided by m1 plus m2 square, okay. So you get m1 m2 square a square plus uh, m2. So here when you combine this, you get m1a over m1 plus m2. So you have m2 times m1 square a square, okay, divided by m1 plus m2 square, okay. So we pull out the common factor, which is m1 m2 a square, and then you have m1 plus m2 divided by m1 plus m2 square, and you cancel the common term, and hence you get the required expression. And as mentioned, I'm going to call this thing, I'm going to call this term mu, okay, yeah, the reduced mass, okay. And then classically, when it comes to um, such rigid rotor, okay, the kinetic energy, okay, or the total energy is just half I omega square, and then you can write it in terms of L square over I, okay, just like P square over 2m, then you have L square over 2I, okay. So the Hamiltonian, okay, H is L square over 2I. And then in quantum mechanics, we know the eigenvalues of L square operator, okay, which is L plus 1 h bar square, right? But since we tend to use n in energy, okay, using n as the quantum number for energy. Okay, then En is h bar square over 2I n times n plus 1. Okay, and n is 0, 1, 2, and so on. Okay, yeah, shown. Okay, so this is for part A. Then we move on to part B. We want to find the normalized eigenfunctions. Okay, so the normalized eigenfunctions, okay, they are the spherical harmonics. Okay, because they are spherical harmonics are the coordinate representation of L square operator. Okay, so the psi and m, theta phi is our y and m. Okay, so basically it's just replacing the L in the YLN with n. Okay, and you get the spherical, then you get the normalized eigenfunctions for this situation. Okay, and we know that from the idea of angular momentum, n will be an integer, okay, between minus n to n. Okay, so n is minus n plus 1, okay, in steps of 1 until you get n minus 1 and n. Okay, so overall over here you have 2n plus 1. Okay, so the degeneracy, okay, is 2n plus 1. Okay, so this is the answer, okay, for part B. Okay. Okay, next in part C, you want to find the spectrum, the energy spectrum of this system. Okay, so the frequency that that is emitted from the emission spectrum will be the change in energy, uh, the, the energy transition between levels. Okay, so okay, so suppose we have transition from n plus 1 level to the nth level. Okay, so our delta E is equal to h bar square over 2I. Okay, so recall that En is h bar square over 2I n times n plus 1. So the delta E would be from n plus 1 to n. This is what I would do. Okay, yeah, so the first term is when you substitute n plus 1 into the n times n plus 1, and then you subtract n times n plus 1. Okay, and so you have h bar square over 2I 2 times n plus 1. Okay, so the n plus 1 is common in the two terms, and then you are left with n plus 2 minus n, and then you are left with 2. Okay, and you can write this as h bar square over I times n plus 1. Okay, so the 2 cancels out. Okay, and delta E is h mu. Okay, and so h bar square over I times n plus 1. Okay, so nu is equal to h bar over 2 pi I n plus 1. Okay, so since n is equal to 0, 1, 2, and so on, so I'm going to call j is equal to n plus 1, and this will be 1, 2, and so on. Okay, so mu j is h bar over 2 pi I j, okay, and j is equal to 1, 2, 3, and so on. Okay, yeah. So yeah, that's how we can arrive at the spectrum. Okay, which is what the hint or the answer that's given in this part. Okay, so that's how we arrive at this answer. Okay. Okay, in part D, we are given the spectrum for the carbon monoxide. So we want to find the frequency separation between adjacent lines. Okay, so from the diagram, we see that there are 11 absorption dips. Okay, so the frequency separation between adjacent lines will be 68 minus 27 divided by 11. Okay, this is equal to 3.73 per cm. And then in the question, we are also given the conversion factor. So to convert to hertz, okay, you multiply by 3 times 10 to the 10. Okay, and then you get 1.12 times 10 to the 11 hertz. Okay, that's the frequency separation. Okay. Right, then we want to calculate the distance between the carbon and oxygen atom in carbon monoxide. So we are given that m of the carbon is 12 U. Okay, and then the mass of the oxygen is 16 U. Okay, so you can calculate the reduced mass. Okay, mu will be m1 mc mo divided by mc plus mo. Okay, so get 12 times 16 u divided by 12 plus 16. Okay, so this is 48 over 7 times u, which is 1.66 times 10 to the negative 27 kg, and you get 1.14 times 10 to the negative 26 kg. Okay, then so for adjacent lines, okay, j equals to 1. Okay, j is for the index in the new j in part C, right? So we have delta, we have mu equals to in part C, okay, h bar over 2 pi I, okay, and our I is pi mu a square. Okay, so we want to obtain a is going to be h bar over 2 pi mu nu, okay, square root. Okay, now you can substitute the numbers. Okay, 1.054 times 10 to the negative 34, that's h bar. Okay, 2 pi, and mu is 1.14 times 10 to the negative 26, and the nu, which is the delta nu. Okay, this is 1.12 times 10 to the 11. After that, you take the square root. Calculate this, you get 1.15 times 10 to the negative 10 meters. Okay. Okay, so this is the answer for part D. Okay, and that's all for this question.